Right now, Lake Powell is holding barely more than 1/5 of its usable capacity, while its surface sits only a few dozen feet above the level where Glen Canyon Dam can no longer generate hydropower normally. That is extraordinary because the reservoir has already passed through the season when melting mountain snow should have rebuilt its defenses. Instead, the river delivered only a fraction of its average flow, and the lake is expected to enter the next water year with roughly 5 million acre-feet remaining, a volume that sounds enormous until it is measured against the demands placed upon it. But that is not the most frightening part. The immediate danger is not an empty lake. It is a shrinking margin between normal operations and physical failure. Each foot lost brings the water closer to turbine intakes, reduces hydropower flexibility, and leaves managers with fewer ways to protect both Lake Powell and Lake Mead. A weak runoff season next year would not begin with a full reservoir. It would begin after much of the emergency buffer had already been spent. So what happens when a system built to absorb several dry years reaches the next one with almost nothing left to absorb it? Viewers following water, climate, and infrastructure risks can like, subscribe, and leave a comment naming the place where they live and the reservoir or river their community depends upon. Standing on the rim above Glen Canyon, the first thing anyone notices is not the dam. It is the silence. The vast blue reservoir that once stretched deep into dozens of sandstone canyons now sits far below the pale white bathtub ring carved into the cliffs, a permanent scar showing where the water used to be. Every exposed layer tells the same story. The lake has been retreating for years, and every season it leaves behind another band of rock that sunlight has only recently touched. For tourists, it is an unforgettable landscape. For engineers, it is a measuring tape counting down toward a critical operating limit. For the millions of people connected to the Colorado River, it is a warning that extends far beyond the shoreline. Lake Powell is not simply another reservoir in the American Southwest. It is one of the largest pieces of water infrastructure ever built in the United States, storing water that supports cities, farms, industries, tribal communities, recreation, ecosystems, and one of the region's most important sources of hydropower. Every foot of elevation lost changes how that entire system functions. Right now, federal water managers are not watching the reservoir because they fear it will suddenly become empty. They are watching because it is approaching the minimum power pool, the elevation where Glen Canyon Dam can no longer generate electricity under normal operating conditions. That distinction matters because losing hydropower would affect far more than the lights connected to the grid. The electricity produced here helps stabilize power demand across the region, especially during periods of extreme summer heat when air conditioners run continuously and electricity consumption reaches its highest levels. Communities supplied through the Colorado River Storage Project depend on that relatively inexpensive hydropower, including rural electric cooperatives, irrigation districts, tribal nations, and public utilities spread across several western states. If that generation disappears, replacement electricity must come from somewhere else, often at higher prices and with less operational flexibility. At the same time, businesses surrounding the lake are confronting another reality. Boat ramps that once reached deep water have required repeated extensions or complete relocation. Marinas have been moved farther into the shrinking reservoir. Tour operators constantly adjust routes that no longer resemble the maps visitors remember from previous decades. Hotels, restaurants, fishing guides, fuel suppliers, and seasonal workers all depend on visitors arriving at a lake that continues to pull away from the infrastructure built around it. Every decline in water level carries economic consequences that ripple through communities whose livelihoods are tied directly to recreation. Downstream, the stakes become even larger. Farmers throughout the Colorado River Basin depend on carefully managed releases from Lake Powell to support irrigation systems that feed crops across some of the most productive agricultural regions in the western United States. Cities including Phoenix, Las Vegas, Los Angeles, Denver, Albuquerque, and many others depend directly or indirectly on the Colorado River system that Lake Powell helps regulate. The reservoir functions like a giant balancing mechanism between the upper basin and the lower basin, ensuring that water deliveries remain as reliable as possible, despite enormous swings in annual snowpack. When that balancing reservoir loses flexibility, every user connected to the river begins operating with a smaller margin for error. Federal agencies have repeatedly emphasized that reservoir operations are entering a period where every decision involves difficult trade-offs rather than easy solutions. Holding additional water inside Lake Powell may help protect hydropower production, but that same water is no longer available to increase storage downstream in Lake Mead. Releasing more water to assist Lake Mead may strengthen one reservoir while weakening another. Protecting one part of the system can increase stress somewhere else, because both reservoirs now operate much closer to their critical thresholds than the engineers who designed them originally expected. This is why official forecasts are followed so closely by water managers across the American West. Each monthly projection is more than a prediction of lake elevation. It is an assessment of how much operating flexibility remains before emergency measures become necessary once again. Viewers watching this story from thousands of miles away may wonder why a reservoir hidden within sandstone cliffs should matter to them. The answer lies in what Lake Powell represents. Around the world, modern societies increasingly depend on infrastructure that was designed using assumptions about climate, water availability, and environmental stability established decades ago. Reservoirs, power plants, irrigation canals, electrical grids, highways, and cities all assume that nature will continue behaving within a familiar range. Lake Powell is revealing what happens when those assumptions begin to fail. The exposed rock surrounding the reservoir is not only marking where the water used to be, it is marking the distance between the world the system was built for and the world it is now being forced to operate within. At this moment, that distance is becoming smaller with every foot the lake declines. And that is why millions of people who may never visit Glen Canyon still have a stake in what happens here next. The human mind struggles to understand slow disasters because they rarely arrive with a single explosive moment. They advance one measurement at a time. 1 foot of elevation disappears. Then another. Another month passes with disappointing runoff. Another federal forecast lowers the expected inflow. Another emergency operating plan is prepared. None of these developments seems dramatic in isolation, yet together they reveal a pattern that is far more alarming than any individual headline. The numbers surrounding Lake Powell tell exactly that story. They are not simply measurements of water. They are measurements of how much flexibility remains before an entire operating system begins to lose its ability to function. Start with the reservoir itself. At full pool, Lake Powell can store roughly 24 million acre-feet of water. An acre-foot is difficult to picture until it is translated into something familiar. Imagine an area the size of a football field covered with water, almost 1 foot deep. Now multiply that volume millions of times. 1 acre-foot equals approximately 326,000 gallons, enough to supply several households for an entire year, depending on local consumption. 24 million acre-feet represents one of the largest artificial water reserves ever created on Earth. Yet today, only a fraction of that storage remains available. The reservoir has fallen to little more than 1/5 of its total capacity. That means nearly 4 out of every 5 units of storage originally designed into the system are no longer filled with water. Even that statistic does not fully explain the danger, because storage volume alone is not what determines operational security. Elevation does. Glen Canyon Dam generates electricity because water falls through massive turbines under tremendous pressure. That pressure depends on the vertical distance between the reservoir surface and the power plant below. As the lake drops, the pressure decreases. Eventually, the water level reaches approximately 3,490 feet above sea level, the minimum power pool. At that elevation, the turbines can no longer operate under normal conditions. Notice what this number does not mean. It does not mean the reservoir is empty. Millions of acre-feet of water may still remain inside the canyon, but much of that water is no longer positioned where existing infrastructure can efficiently transform it into electricity. The reservoir may still appear enormous from the air, while one of its most important functions has already disappeared. That distinction changes the entire conversation. Another number deserves equal attention. During an average year, melting snow across the upper Colorado River basin delivers enough runoff to replenish a meaningful portion of Lake Powell's storage. But this year, the river has behaved very differently. Federal projections indicate that inflow into the reservoir has been only a small fraction of the historical average. Some forecasts have estimated natural inflow at roughly 1/3 of normal conditions. Imagine a business expecting $100 in revenue and receiving only 36. Imagine a farmer expecting 100 truckloads of water and receiving only 36. Imagine an emergency savings account built to survive several difficult years, suddenly receiving only 1/3 of the income required to refill it. The mathematics quickly become unforgiving because the reservoir cannot spend water it never receives. Another comparison reveals why these percentages matter so much. A difference of 20 or 30 feet in lake elevation may sound insignificant when viewed against canyon walls hundreds of feet high. Yet those few dozen feet represent the entire operating buffer, separating normal hydropower production from one of the most serious engineering thresholds in the reservoir's history. If a commercial airplane were descending toward a runway, passengers would not consider the final few dozen feet unimportant. Those final feet determine whether the aircraft lands safely or strikes the ground. Lake Powell is approaching the hydraulic equivalent of that final approach. Every additional foot now carries more operational significance than many of the hundreds of feet lost earlier in the drought, because the remaining safety margin is becoming progressively smaller. The numbers become even more striking when viewed across time rather than space. Reservoirs traditionally follow a seasonal rhythm. Snow accumulates through winter, melts during spring, raises lake levels during early summer, and then gradually declines as water is released downstream and consumed throughout the hotter months. Managers expect that cycle. It is built into every operating plan. But when spring runoff repeatedly fails to restore the reservoir to healthier elevations, each new year begins from a lower starting point than the year before. The system slowly loses its ability to recover. That is exactly what concerns hydrologists. A reservoir does not enter crisis only because one year is dry. It enters crisis when several years gradually erase the recovery that previous wet years once provided. Every weak runoff season consumes another portion of the emergency reserve. Every exceptionally hot summer increases evaporation and plant water use throughout the watershed. Every disappointing snowmelt leaves less flexibility for the following year. Suddenly, the most important number is no longer today's elevation. It becomes tomorrow's starting elevation. That is why experts are paying such close attention to projections extending into the next water year. A single favorable winter could temporarily improve conditions. A second consecutive poor runoff season, however, would begin with the reservoir already operating dangerously close to its critical threshold. This is the mathematical reality hidden beneath the headlines. The danger is not one dramatic number. It is the relationship between all of them. Storage is lower, elevation is lower, inflow is lower, recovery is weaker. Operating flexibility is shrinking. When every trend points in the same direction at the same time, the numbers stop describing a reservoir. They begin describing a system that is gradually consuming its own margin of safety. That is why Lake Powell is no longer simply a story about water levels. It has become a story about disappearing resilience, measured 1 foot, 1 forecast, and 1 difficult decision at a time. The most obvious way to describe Lake Powell is to say that it is running out of water. That description is not entirely wrong, but it misses the deeper danger. The real threat is not simply the amount of water remaining in the reservoir. It is the shrinking distance between that water and the infrastructure built to use it. A reservoir can still contain an immense volume and yet lose critical functions long before it becomes empty. That is the hidden turning point in this story. Lake Powell does not have to disappear for the system around it to begin failing. It only has to fall below the elevations where water can move through the dam in the way engineers intended. For decades, public attention has focused on the white bathtub ring, the abandoned boat ramps, the exposed canyon walls, and the dramatic images of a shrinking lake. Those images are powerful because they make decline visible. But the most important structures are hidden below the surface. Massive steel penstocks carry water toward the turbines. Intake openings depend on the reservoir remaining high enough to maintain sufficient pressure. Generators depend on that pressure to spin efficiently. Operators depend on predictable flows to balance electricity production with downstream water deliveries. Every one of those functions was designed around a range of lake elevations. Once the reservoir moves outside that range, the problem changes. It is no longer only a drought problem. It becomes an infrastructure problem. The critical concept is hydraulic head, the vertical distance that gives falling water its power. Glen Canyon Dam does not create electricity simply because water exists behind it. It creates electricity because that water sits hundreds of feet above the turbines. Gravity converts the height of the reservoir into pressure. The greater the elevation difference, the more forcefully water can move through the turbines. As the lake drops, that pressure weakens. The turbines become less efficient. Their generating capacity declines. Eventually, the reservoir approaches the point where normal power production can no longer continue. This is why a few dozen feet can matter more than millions of gallons. The water remains present, but its position has changed. It is like fuel sitting inside a tank below the level of the pipe designed to draw it out. The resource has not vanished, yet the machine can no longer access it in the same way. That is the overlooked mechanism. Lake Powell is not merely losing volume, it is losing useful elevation. The distinction is crucial because elevation determines which parts of the system remain available. Above minimum power pool, managers can release water through the turbines while producing electricity. Below that threshold, they must rely increasingly on other outlet structures that were not designed to replace normal power operations over long periods. These bypass systems can move water downstream, but they do not provide the same energy benefits, the same flexibility, or necessarily the same operating security. Their role was intended for maintenance, emergencies, and specialized releases, not as the permanent main channel for one of the most important reservoirs in the West. This is where the danger stops being abstract. If hydropower production is lost, the immediate consequence is not necessarily a regional blackout. Other power plants can supply electricity, markets can purchase replacement energy, grid operators can adjust, but every replacement carries a cost, and every substitute removes another layer of flexibility. Hydropower is valuable not only because it generates electricity, but because it can respond quickly. When temperatures surge and millions of air conditioners switch on, hydroelectric generators can increase output rapidly. When solar power falls in the evening, hydropower can help fill the gap. When another generator unexpectedly fails, dams can respond in minutes. Losing Glen Canyon's generation would therefore remove a tool that becomes most valuable during the same extreme heat conditions that are helping intensify water loss across the basin. The system would not necessarily break in one dramatic moment. It would become more brittle. Electricity providers would depend more heavily on power purchased elsewhere. Rural cooperatives and tribal utilities could face higher costs. Grid operators would have fewer fast response resources. Another heat wave, another transmission problem, or another power plant failure would arrive in a system with less room to maneuver. This is why the headline number can be misleading. The question is not how much water remains in Lake Powell. The question is how many functions remain available at each elevation. The first major function at risk is hydropower. But it is not the last. The dam also regulates water moving from the upper basin toward the lower basin. That water supports Lake Mead, Hoover Dam, farms, cities, and international delivery obligations farther downstream. As the lake approaches lower operating levels, the challenge of releasing water safely and predictably becomes more complicated. Managers are forced to examine outlet capacities, water pressure, vibration risks, sediment behavior, cavitation, and other engineering concerns that rarely enter public discussion. None of these issues means the dam is about to collapse. That would be an unsupported claim. The real concern is more subtle and more credible. Infrastructure becomes harder to operate when it is forced into conditions it was never expected to face for extended periods. Equipment that works reliably within its design range can behave differently at the edge of that range. Flow patterns change, pressures change. Maintenance becomes more urgent. Options narrow. The dam remains standing, but the system around it becomes increasingly dependent on fewer pieces of equipment. That is how large networks often fail. They do not collapse because every component breaks at once. They become fragile when too much responsibility shifts onto one remaining pathway. At Lake Powell, the small component with enormous consequences is not the entire dam. It is the elevation of water relative to specific intake structures. A change measured in feet can determine whether thousands of megawatts of generating capacity remain available, whether water releases pass through turbines or bypass them, and whether managers can continue balancing the needs of two giant reservoirs using familiar rules. That is why the reservoir's approach toward minimum power pool deserves more attention than the dramatic but distant idea of a completely empty lake. Dead pool, the point where water can no longer flow through the dam by gravity, sits lower than the minimum power pool. The reservoir could therefore lose electricity generation while still holding an enormous quantity of water. That intermediate state is the dangerous one because it creates the illusion that the system still has time. From a viewpoint above the canyon, Lake Powell would still look vast. Boats could still move across parts of the reservoir. Blue water would still stretch toward the horizon. Yet beneath that surface, a central function of the dam could already be gone. The visible landscape would lag behind the invisible failure. This is also why next year matters more than the current headline suggests. If the reservoir reaches the end of this water year close to the power threshold, it will begin the next cycle with a weakened buffer. A strong snow season could lift the lake and buy time. But another weak season would not begin from a position of safety. It would begin with the reservoir already close to the elevation, where each additional foot carries disproportionate consequences. Managers could hold back more water in Lake Powell, but doing so would reduce releases toward Lake Mead. They could release water from upstream reservoirs, but that would draw down storage intended to protect other communities and future years. They could reduce deliveries, but every reduction would trigger political, economic, and legal conflict. Each option protects one part of the system by placing more pressure on another. That is the defining feature of a system running out of buffer. Solutions stop being solutions. They become transfers of risk. The hidden danger, then, is not simply a lower lake. It is a narrowing corridor of acceptable choices. Every foot lost closes another door. Every emergency measure consumes a resource that may be needed later. Every attempt to protect hydropower can weaken downstream storage. Every attempt to maintain downstream releases can accelerate the approach toward minimum power pool. The reservoir is not moving toward one dramatic edge. It is moving into a zone where every decision carries larger consequences, and fewer reversals are possible. That is what the white line on the canyon wall cannot show. It records where the water once stood, but not how many operating options have disappeared with it. The real crisis is not that Lake Powell may someday become empty. The real crisis is that the system can begin losing essential functions while the reservoir still appears enormous, while millions of acre-feet remain trapped below critical elevations, and while the public believes there is still plenty of water left. Word count: 1,437. The mechanism driving Lake Powell toward its operating limits begins hundreds of miles away from the dam, high in the mountains where winter storms deposit snow across the upper Colorado River basin. That snow is the true reservoir. Long before water enters the Colorado River, long before it reaches Glen Canyon, and long before it spins a turbine, it is stored as ice in forests, alpine meadows, and steep mountain valleys. For generations, this frozen storage system released water slowly enough to sustain rivers through spring and early summer. Engineers built the modern Colorado River system around that rhythm, Snow accumulated during winter. Temperatures rose in spring. Meltwater entered streams. Reservoirs filled. Releases were scheduled. Farms planted. Cities planned. Power systems counted on water, arriving within a familiar seasonal window. But the rhythm is changing, and the central mechanism is not simply drought. It is aridification, the long-term drying of a region as rising temperatures increase the amount of water demanded by soil, plants, and the atmosphere. A drought is usually understood as a temporary shortage, a period when precipitation falls below normal and conditions eventually recover. Aridification is more persistent. It changes what normal means. Even when snowfall appears near average, the amount of water reaching rivers can still be lower because a warmer landscape takes a larger share before the runoff ever arrives at Lake Powell. This is the hidden journey of missing water. It begins in the atmosphere, moves into the snowpack, passes through dry soil and vegetation, and ends as a reduced flow entering the reservoir. The first step is temperature. Warmer air holds more water vapor and creates a stronger demand for moisture from the land surface. Scientists describe part of this demand as vapor pressure deficit, a measure of how strongly the atmosphere pulls water from soil and plants. The term sounds technical, but the image is simple. Dry air behaves like a larger sponge. The warmer and drier that sponge becomes, the more aggressively it draws moisture from everything beneath it. Forests release more water through their leaves. Soil loses moisture more rapidly. Snow can evaporate or sublimate directly into the atmosphere. Rivers receive less of what fell during winter. The water has not vanished in a physical sense. It has changed pathways. Instead of traveling downhill into the Colorado River, a greater fraction travels upward into the air. That shift can occur across millions of acres at once, turning a modest change in temperature into an enormous loss of runoff. The second step happens inside the soil. After a dry summer and autumn, the ground enters winter, carrying a moisture deficit. When spring snow begins to melt, the first water does not immediately rush towards streams. It soaks downward. The soil absorbs it like a dry sponge placed beneath a dripping faucet. Before the river can receive its share, the landscape must repay the moisture debt accumulated during previous hot months. In a cooler and wetter system, that debt may be small. In a hotter system, it can consume a substantial portion of early snowmelt. This is why an apparently healthy mountain snowpack can produce disappointing runoff. The snow gauge measures water stored above the ground. It does not automatically reveal how much of that water will survive the journey through the ground. A basin can therefore enter spring with encouraging snow totals and still deliver far less water than managers expect. The third step is vegetation. Trees, shrubs, and grasses pull water through their roots and release it into the atmosphere through transpiration. This is a normal and necessary process, but higher temperatures can extend the growing season and increase total water use. Plants may begin drawing moisture earlier in spring and continue later into autumn. Across a vast watershed, those extra days matter. Each individual tree releases only a small amount at a time, but entire forests function like biological pumps. They move water from soil into the atmosphere continuously. When heat increases that pumping, less water remains available to enter streams. In areas affected by wildfire, insect damage, or forest change, the response can be even more complicated. Some disturbances reduce vegetation and temporarily lower transpiration. Others alter snow accumulation, soil structure, erosion, and runoff timing. The outcome varies by location, but the larger point remains the same. Water does not move from snowpack to reservoir through an empty pipe. It passes through a living landscape that consumes, stores, redirects, and releases it. The fourth step is timing. Snow that melts earlier does not always provide the same benefit as snow that melts later. Historically, high mountain snowpack acted like a slow-release bank account. It stored winter precipitation and distributed it over several months. Warmer spring temperatures can accelerate that release. The runoff arrives earlier, sometimes before agricultural demand reaches its peak and before reservoir operators would prefer to store or release it. Earlier melt also leaves the landscape exposed to a longer hot season. Rivers decline sooner. Soil dries earlier. Plants begin drawing more water, while summer heat is still ahead. A snowpack that disappears quickly can therefore produce a short pulse of runoff, followed by an extended period of low flow. The total amount of snow may look respectable, yet the seasonal pattern becomes less useful. Water arrives at the wrong time and leaves too soon. This is not merely a forecasting inconvenience. It changes how reservoirs must be operated. Lake Powell is designed to smooth out fluctuations, but even a giant reservoir cannot fully compensate when inflows repeatedly arrive earlier, weaker, or more unevenly than the rules assumed. The fifth step is evaporation. Lake Powell itself loses water directly to the atmosphere. So do upstream reservoirs, rivers, canals, soil surfaces, and irrigated fields. Evaporation is not a new problem in the desert Southwest, but higher temperatures intensify it. A broad reservoir surface exposed to sun and wind becomes a continuous source of moisture to the air. The exact loss varies from year to year, depending on temperature, wind, humidity, and surface area, but the direction of pressure is clear. The hotter the system becomes, the more water must be stored simply to preserve the same usable volume. This creates a cruel feedback. As the reservoir shrinks, some exposed areas reduce evaporation because less water surface remains. But the water that does remain is still subject to intense atmospheric demand, while the entire watershed above the lake is also losing more moisture. Lake Powell is therefore receiving less water from the mountains, while continuing to lose water at its own surface. It is being squeezed from both directions. Scientists often describe the combined result as declining runoff efficiency. That phrase means the same amount of precipitation produces less river flow than it once did. Consider a simplified example. Suppose 100 units of water fall as snow across a mountain basin. In a cooler period, perhaps a large share of those units survives long enough to enter streams. In a warmer period, more is absorbed by dry soil, used by vegetation, lost through evaporation, or released at a time when it cannot be stored as effectively. The snow gauge may still record 100 units, but the river receives fewer. This is why snowpack percentage and runoff percentage are not interchangeable. A basin can report snow near its historical average, while inflow into Lake Powell remains far below average. The missing water is not necessarily a measurement error. It has been intercepted by a warmer landscape. That interception is one of the most important changes now confronting the Colorado River Basin, because it weakens the predictive relationships used for decades. Water managers once relied heavily on snowpack as a guide to future runoff. That relationship still matters, but temperature, soil moisture, vegetation, dust on snow, storm timing, and spring heat now exert greater influence over the final result. Dust provides a vivid example. When wind carries dark particles onto mountain snow, the surface absorbs more sunlight. The snow warms and melts faster. A thin layer of dust can alter the timing of runoff across a large region. The meltwater may arrive earlier and more quickly, leaving less snow to sustain rivers later in the season. Dust is not the sole cause of Lake Powell's decline, but it shows how a small physical change can move through the entire system. Dark particles settle on snow. Snow absorbs more energy. Melt accelerates. Soil dries sooner. Rivers peak earlier. Reservoir inflow weakens later. A process, beginning with a barely visible layer on a mountain, can ultimately affect the pressure available at a turbine hundreds of miles downstream. This is how the mechanism must be understood, not as one isolated cause, but as a chain. Heat changes the atmosphere. The atmosphere pulls more water from the land. Dry soil captures more snowmelt. Plants use water for longer periods. Snow melts earlier. Runoff efficiency falls. River inflow declines. Lake elevation drops. Hydraulic head weakens. Hydropower production becomes less secure. Replacement electricity becomes more expensive. Those costs reach utilities, irrigation districts, tribal communities, and households. The path begins with temperature and ends inside a monthly budget. It begins in mountain snow and ends in a power market. It begins as a climate signal and becomes an infrastructure problem. That is the part often lost when Lake Powell is discussed only through photographs of exposed canyon walls. The reservoir is not shrinking because of one bad winter alone. It is shrinking because the entire route from sky to river has become more demanding. Every stage takes a share. The atmosphere takes more. The soil takes more. Vegetation takes more. Human withdrawals continue. By the time the remaining water reaches the reservoir, it enters a system already responsible for cities, farms, ecosystems, treaty obligations, and power production. Lake Powell is not the first place the shortage appears. It is where all the upstream losses become visible at once. This also explains why one wet year cannot automatically solve the problem. A powerful winter can raise the reservoir and provide temporary relief. It can restore some operating margin, improve hydropower conditions, and reduce immediate pressure. But if the underlying landscape remains hotter, that wet year still loses more water than an equivalent year might have lost decades earlier. The basin can receive a generous deposit, while the account continues, charging a higher fee on every transaction. The reservoir rises, but perhaps not enough. The crisis retreats, but the mechanism remains. Then the next dry year begins from a weaker position. This is the difference between variability and a changing baseline. Variability determines whether a particular winter is wet. The baseline determines how much water survives either kind of winter. In a warming basin, a dry year becomes more damaging because the landscape intensifies the loss. A wet year may become less effective at rebuilding storage because a larger fraction of the water is consumed before it reaches the river. The same weather event produces a different hydrological outcome. That is why the phrase megadrought, while useful, can sometimes hide the deeper process. It suggests a very long version of a familiar drought, something severe but ultimately temporary. Aridification suggests something more difficult. A region moving toward a drier state, in which old averages no longer describe current reality. The distinction matters for policy. A temporary drought can be survived by drawing down reservoirs and waiting for normal conditions to return. Aridification requires reducing demand, changing operating rules, redesigning infrastructure, and accepting that the past may not return on schedule. Lake Powell was built to store abundance from wet years and release it during dry years. But that strategy depends on wet years producing enough surplus to replace what dry years remove. When warming reduces the surplus, the reservoir becomes a one-way account. Withdrawals continue, deposits weaken, the balance falls. At first, the decline looks manageable because the account is enormous. Then the buffer narrows. Then the system begins protecting minimum thresholds rather than planning for prosperity. That transition is already visible. Managers are no longer asking only how to divide a full river. They are asking how to prevent critical reservoirs from crossing elevations that threaten power generation and water delivery. The language of management shifts from allocation to protection, from optimization to emergency response. And beneath every emergency decision lies the same physical mechanism. Too little of the water falling over the basin is completing the journey to Lake Powell. The most powerful image is not the dry bathtub ring. It is a snowflake landing in the Rocky Mountains and facing an obstacle course before it can become electricity. It must survive warmer air. It must survive an early melt. It must pass through thirsty soil. It must escape plant roots. It must reach a stream. It must travel through upstream reservoirs and diversions. It must enter the Colorado River. It must arrive at Lake Powell in enough quantity to raise the surface. Only then can gravity carry it through Glen Canyon Dam and turn a turbine. Every additional degree of heat makes that journey harder. Every dry season increases the number of places where the water can be lost. Every year of weak inflow lowers the starting point for the next one. The crisis at Lake Powell is therefore not created at the shoreline. It is assembled across the entire basin, molecule by molecule, as water is diverted from the path the infrastructure depends upon. That is the central mechanism. The reservoir is not simply being drained from below, it is being starved from above. History has already shown what happens when the Colorado River system begins consuming its safety margin faster than nature can rebuild it. And the warning did not begin with the current descent of Lake Powell. It began near the start of the 21st century, when a sequence of dry years exposed how quickly a reservoir that appeared almost limitless could lose the water accumulated over decades. At the beginning of the modern drought, Lake Powell still carried the visual authority of a full reservoir. Its marinas floated near infrastructure built for high water, its turbines operated with abundant hydraulic pressure, and its immense storage concealed the imbalance developing across the basin. Then the inflows weakened. Releases continued. The shoreline retreated. Within only a few years, a reservoir that had taken roughly 17 years to fill surrendered a vast portion of its stored water. That decline established the first historical lesson. Large storage creates time, but it does not create new water. A reservoir can postpone the consequences of shortage so effectively that the public mistakes delayed impact for permanent security. During the first major years of decline, Lake Powell performed exactly as its designers intended. It released water when the river delivered less. It protected downstream obligations. It generated electricity. It absorbed the drought. But every successful year of protection lowered the reservoir further, transforming stored water from a shield into a countdown. The drought that began around the year 2000 did not behave like a short interruption, followed by a complete recovery. Wet years arrived, and some were impressive, but they were repeatedly followed by renewed losses. The reservoir rose, then fell again. Each recovery encouraged the belief that the system had turned a corner. Each subsequent decline revealed that the underlying balance had not changed. The river was still being asked to support commitments larger than the water it reliably produced. This pattern became especially severe during the years leading into 2022. Lake Powell descended toward elevations that had once appeared almost theoretical in operating documents. In March of that year, the reservoir fell below 3,525 feet, leaving less than 35 feet between the lake and minimum power pool. That elevation was not chosen because failure would occur immediately at that exact line. It was chosen as a protective target, a narrow buffer designed to give managers time to respond before the reservoir reached approximately 3,490 feet, where normal hydropower generation would be threatened. The system was no longer using Lake Powell primarily to maximize water and electricity benefits. It was using emergency measures to defend the machinery from the lake itself. Federal managers reduced releases from Glen Canyon Dam, adjusted the timing of downstream deliveries, and called on upstream reservoirs to send additional water toward Powell. Flaming Gorge Reservoir, far upstream on the Green River, became part of the rescue. Water stored behind another dam, intended to serve other purposes and protect other years, was released so that Lake Powell could remain above its critical elevation. Additional water also came from Blue Mesa and Navajo reservoirs during earlier response actions. The decision proved that the basin possessed emergency flexibility, but it also revealed the true nature of that flexibility. The water was not created, it was moved. Protection at Lake Powell required drawing down storage somewhere else. One reservoir's safety margin became another reservoir's sacrifice. Communities near Flaming Gorge watched their own shoreline decline, so that turbines hundreds of miles downstream could retain enough pressure to operate. That was not a failure of management. Under the circumstances, it was a rational emergency action. But emergency actions reveal the architecture of a crisis. They show where the remaining reserves are located and how quickly those reserves can become obligations. The year 2023 then delivered the kind of winter the basin desperately needed. Snow accumulated across the upper Colorado River basin, runoff strengthened, and Lake Powell rose dramatically from its recent lows. Images of returning water produced relief. Boat ramps reopened. The distance above minimum power pool expanded. Headlines suggested that the crisis had eased. In one important sense, it had. The strong runoff bought time and restored part of the reservoir's operating buffer. Yet the recovery also created a dangerous misunderstanding. A rising lake was treated by some observers as evidence that the long drought had ended, even though the reservoir remained far below full pool and the larger water balance remained unresolved. One wet year changed the elevation. It did not change the amount of water legally promised across the basin. It did not erase the previous 2 decades of declining storage. It did not remove the warming influence that causes more snowmelt to be absorbed by soil, vegetation, and the atmosphere. It did not guarantee another strong winter. The rebound demonstrated the power of natural variability, but it also demonstrated the limits of recovery. A reservoir can gain dozens of feet in a favorable year and still remain vulnerable to the next sequence of weak inflows. Researchers examining tree rings and reconstructed soil moisture have extended this history far beyond modern reservoir records. A major study published in 2022 concluded that the period from 2000 through 2021 was the driest 22-year interval in southwestern North America since at least the year 800. The reconstruction did not claim that human-caused warming created every dry winter or controlled every storm. It showed something more precise. Natural variability produced a severe drought, while human-caused warming intensified it by increasing moisture loss from the landscape. The study estimated that warming contributed roughly 1/5 of the drought severity during that period. That distinction matters because it prevents 2 opposite errors. The first is claiming that climate change caused the entire event. The second is claiming that climate change played no role because ancient megadroughts also occurred naturally. The evidence supports neither extreme. The Southwest has always experienced prolonged drought, but modern warming adds heat to those natural dry periods, making the soil drier, increasing evaporative demand, and reducing the likelihood of rapid recovery. Another body of research has examined the Colorado River itself, rather than regional soil moisture. Studies have found that rising temperatures have already reduced upper Colorado River flow, even when changes in precipitation alone cannot explain the full decline. One analysis concluded that long-term climate forcing reduced stream flow by roughly 10% over the period it studied, with natural variability accounting for another share of the observed change. Earlier work by researchers Bradley Udall and Jonathan Overpeck estimated that warming during the early 21st century reduced Colorado River flow by at least 500,000 acre-feet, a volume comparable to the annual water use of millions of people under common household estimates. These figures are not identical because the studies examine different periods, methods, and definitions. Science does not offer one perfect number describing how much water warming has removed from the Colorado River. It offers a range of evidence pointing in the same direction. Heat is turning precipitation into less runoff. More recent research has added another unsettling finding. The probability that drought conditions will recover has declined in recent decades, partly because warmer non-winter months increase atmospheric demand for water. In other words, the system is not only entering drought more dangerously, it may also require longer to escape. That finding helps explain why the brief recoveries at Lake Powell have not restored the security that once followed a wet cycle. The basin can receive snow, generate a strong runoff year, and raise the reservoir, yet still remain inside a broader period of depleted soil moisture, elevated temperatures, and reduced storage. Recovery is no longer a switch that turns drought off. It is a ladder, and each hotter year removes another rung. A useful comparison comes from California, where Lake Oroville fell so low during the 2021 drought that the Edward Hyatt power plant stopped generating electricity for the first time since the facility began operating. The reservoir was not empty. The dam did not fail. California's electrical grid did not collapse, but the water level fell below what the hydropower system needed, proving that functional failure can arrive while a large amount of water remains visible behind a dam. That event was smaller in scale than the potential loss of generation at Glen Canyon, yet the mechanism was the same. The reservoir crossed an elevation threshold, and infrastructure lost a service before the public image of an empty lake appeared. Lake Oroville later recovered as precipitation returned, but its shutdown remains a technical precedent. Hydropower is conditional. It depends not merely on water volume, but on water height, intake geometry, pressure, and the operating range of machinery. Glen Canyon Dam is not exempt from those physical laws because it is larger. Its scale only increases the consequences. The comparison also provides a reason for caution rather than panic. Oroville's temporary shutdown showed that a power system can compensate, managers can respond, and generation can return when reservoir levels recover. But it also showed that waiting until the threshold is crossed forces the system to absorb costs that earlier conservation or stronger buffers might have avoided. Lake Powell's present danger is therefore neither unprecedented nor imaginary. Each piece has appeared before. The basin has endured prolonged drought. Lake Powell has approached critical elevation. Upstream reservoirs have been used to protect it. A wet winter has produced a dramatic but incomplete recovery. Scientific studies have measured warming-related flow loss. Another major western reservoir has already lost hydropower because its water fell too low. What has not yet happened at Glen Canyon is the convergence of all these precedents into one event. That is why history matters. It does not provide a perfect copy of the future. It provides the components. It shows how quickly storage can decline, how temporary a rebound can be, how emergency water transfers consume protection elsewhere, and how a reservoir can lose function long before it looks empty. The current approach toward minimum power pool is not a speculative disaster invented from a computer model. It is the next logical stage of a process the basin has already experienced in fragments. The past has delivered every warning separately. The danger now is that Lake Powell may deliver them together. The danger at Lake Powell becomes more serious when the reservoir is viewed not as a single body of water, but as the central joint inside a network of systems that depend on one another. A lake level can be measured in feet, yet the consequences travel through power lines, irrigation canals, municipal budgets, tribal utilities, agricultural markets, and household decisions. The most vulnerable point is not always the largest structure. It is often the small connection that allows the larger structure to keep functioning. The turbine intake that requires sufficient water pressure, the transmission contract that assumes federal hydropower will remain available, the irrigation pump that depends on affordable electricity, or the community budget that has no room for another sudden increase in operating costs. When Lake Powell loses elevation, pressure moves through each of those connections. Glen Canyon Dam contains 8 hydroelectric generators, but their value cannot be measured only by the amount of electricity they produce in a typical year. Hydropower has a quality that many other sources do not possess. Operators can adjust generation quickly. Water can be sent through turbines when demand rises, then reduced when other sources become available. That flexibility helps stabilize an electrical grid in which supply and demand must remain balanced every second. Solar power can fall rapidly when clouds arrive or when the sun sets. A thermal power plant may require hours to change output significantly. A dam can respond much faster, provided enough water remains above the turbines. This makes Glen Canyon especially valuable during hot western afternoons and evenings, when millions of cooling systems are operating and the grid is already under stress. If the reservoir falls below minimum power pool, the first result would not necessarily be darkness spreading across the southwest. The electrical system has other generators, transmission connections, energy markets, and emergency procedures. But the disappearance of Glen Canyon generation would remove a fast and comparatively inexpensive source of power at precisely the moment when the region is confronting longer heat waves, higher cooling demand, and greater pressure on other infrastructure. The grid would continue operating, but with one fewer shock absorber. Replacement energy would need to be purchased from other suppliers. During mild conditions, that replacement might be available without an obvious public crisis. During a widespread heat wave, when many states are competing for the same electricity, prices can rise sharply, and spare generating capacity can become scarce. The risk, therefore, does not come from one failed dam producing an immediate continental blackout. It comes from a system entering its most demanding periods with less flexibility, fewer low-cost options, and a greater dependence on everything else working correctly. The people most exposed to that change are not necessarily the people with the largest homes or the highest electricity use. Federal hydropower from the Colorado River Storage Project is marketed to cities and towns, public utilities, rural electric cooperatives, irrigation districts, tribal nations, and government agencies across a broad section of the West. Together, the project's resources provide electricity on a scale comparable to the annual use of more than 1 million homes. Some customers are small organizations serving wide rural territories with limited financial reserves. Others provide electricity to communities where poverty rates are high, infrastructure investment has been delayed, and extreme heat already creates serious health risks. When inexpensive federal hydropower becomes less available, these utilities may have to buy more expensive replacement electricity on the open market. That cost does not disappear. It enters rate cases, local budgets, irrigation fees, public services, and eventually household bills. Consider how the mechanism can move through one family. Lake Powell drops. Glen Canyon produces less electricity. A small utility purchases replacement power at a higher price. Rates rise, or the utility delays maintenance to contain costs. A household facing extreme summer heat receives a larger bill. The family reduces air conditioning use to protect money needed for food, medicine, fuel, or rent. Indoor temperatures rise during the night, preventing the body from recovering from daytime heat. A water shortage that began as weak mountain runoff has now entered a bedroom hundreds of miles away. It has moved from snow into soil, from soil into the river, from the river into reservoir elevation, from elevation into electricity prices, and from electricity prices into human health. That chain will not affect every customer in the same way, but inequality determines who has the least room to absorb it. Wealthier households can pay higher rates, install efficient cooling systems, or add rooftop solar and batteries. Lower-income households often live in older buildings with weaker insulation, inefficient air conditioners, and fewer options for reducing consumption safely. A modest change in the cost or reliability of electricity therefore becomes a larger threat for the people already living closest to the edge. Tribal communities face an especially complicated form of exposure. Many tribes hold legally recognized or unresolved rights to Colorado River water, while simultaneously confronting inadequate delivery infrastructure, limited access to capital, and high energy costs. Some receive power connected to federal hydropower programs. Some communities within the basin still lack universal access to reliable household water, even as enormous volumes pass through dams, canals, and aqueducts, serving distant cities and farms. The decline of Lake Powell does not create these inequalities, but it can intensify them. When water and power become scarcer, systems usually protect established infrastructure first because established infrastructure already has pipes, contracts, pumping stations, legal teams, and political influence. A community that has waited decades for basic water infrastructure enters the shortage with fewer physical and institutional defenses. This is why the danger cannot be understood by calculating only the reservoir's percentage of capacity. The same missing acre-foot has different consequences depending on who was expecting to use it and what alternatives remain available. Agriculture creates another pathway of vulnerability. Farms across the Colorado River Basin depend on both water and energy. Water must be diverted, lifted, pressurized, transported, and applied. In some irrigation districts, pumps move enormous volumes across long distances or significant changes in elevation. When electricity costs rise, the cost of delivering water can rise with them. Farmers then face a choice between absorbing the expense, changing crops, reducing planted acreage, or passing part of the cost through the food system. The largest agricultural operations may have access to credit, water portfolios, efficiency investments, and political representation. Smaller farms may not. A reservoir decline can therefore move from a turbine into an irrigation pump, from the pump into a planting decision, from the field into farm income, and from farm income into the survival of a rural community. The weak point may be a single season's operating loan or a narrow planting window. Once that window closes, Additional water arriving later cannot restore the crop that was never planted. The system contains many such deadlines. Electricity must be available when heat arrives. Irrigation must be delivered when plants need it. Reservoir releases must meet environmental, legal, and operational requirements at particular times. A shortage is not determined only by annual totals. Timing decides whether the remaining resource can still perform its function. The physical relationship between Lake Powell and Lake Mead creates an even larger vulnerability. The two reservoirs are often described as separate stores of water, but operationally they behave more like chambers in the same failing battery. Water retained in Powell may protect Glen Canyon's turbines and preserve elevation in the upper basin. That same decision reduces the amount moving downstream toward Mead. Less water in Mead can reduce generation at Hoover Dam and increase pressure on lower basin users. Releasing more from Powell can improve conditions downstream while pushing Glen Canyon closer to minimum power pool. There is no adjustment that creates additional water for both reservoirs. Managers are moving a limited volume between competing thresholds. Protecting one piece can expose another. This is the moment when emergency management becomes risk transfer. If additional water is released from upstream reservoirs, such as Flaming Gorge, to support Powell, the visible crisis at Glen Canyon may ease, but storage declines farther north. Those upstream reservoirs support recreation, local economies, ecosystems, power production, and future drought protection of their own. The rescue water travels downstream only once. After it is used to defend Lake Powell, it cannot remain available as insurance against the next dry year in the basin where it originated. The entire system becomes a line of communities passing a shrinking reserve from one vulnerable point to another. The most technically sensitive connection lies inside Glen Canyon Dam itself. Under normal conditions, much of the water released downstream passes through the power penstocks and turbines. Below minimum power pool, hydropower would be lost, and the dam's ability to release water would be reduced. Other outlet structures exist, including river outlet works, commonly described as bypass tubes, but their presence should not be mistaken for a complete substitute for normal operations. Moving water through a bypass does not generate electricity, and relying more heavily on a narrower set of outlet structures reduces redundancy. The engineering concern is not that the dam suddenly becomes unsafe the instant it crosses one elevation. The concern is that fewer pathways remain available. Each pathway carries more responsibility, and operators have less freedom to respond to maintenance needs, environmental requirements, unexpected equipment problems, or further declines. A resilient system survives because it has alternatives. A fragile system may still function, but only as long as the remaining alternative does not fail. This is why the minimum power pool is more than a hydropower threshold. It is the boundary between a dam operating through its primary design and a dam increasingly dependent on secondary pathways. Below that level, each additional decline can further constrain releases. If water cannot be moved downstream at the rate required, the consequences spread into Lake Mead, interstate commitments, deliveries to Mexico, Grand Canyon ecosystems, and the legal structure governing the river. Water may still remain behind Glen Canyon Dam, yet the capacity to place that water where and when it is needed becomes weaker. The reservoir becomes like a warehouse filled with supplies behind a loading door that is gradually becoming too small to serve the entire region. The inventory exists. Access is failing. Environmental systems also sit inside this network of dependence. Releases from Glen Canyon shape water temperature, sediment movement, beaches, fish habitat, and flows through the Grand Canyon. Changes made to protect reservoir elevation or manage outlet limitations can alter downstream conditions. Some effects may benefit one species while harming another. Warmer water released from a lower reservoir can support the expansion of non-native fish that threaten native species. Reduced flexibility can make carefully timed environmental flows more difficult. The dam is therefore not balancing only water and electricity. It is balancing legal deliveries, power demand, recreation, endangered species, sediment, temperature, and the physical limitations of its own machinery. As the reservoir falls, the number of objectives remains the same, while the tools available to meet them decline. This is why the crisis is more dangerous than its headline number. 3,490 feet appears precise and contained. It suggests one threshold, one facility, and one technical problem. In reality, that elevation is a switch connected to dozens of systems. On one side, Glen Canyon Dam can move much of its released water through turbines, produce valuable electricity, and retain greater operational flexibility. On the other side, generation disappears, replacement costs rise, outlet choices narrow, downstream management becomes harder, and pressure is transferred to other reservoirs and communities. The lake does not need to be empty. The West does not need to run completely out of water. The system only needs to lose enough margin that an ordinary disruption becomes an extraordinary emergency. A failed transformer during a heat wave is manageable when electricity is abundant and replacement power is cheap. It becomes more dangerous when hydropower has already disappeared and regional demand is at its peak. A maintenance closure at an outlet is manageable when several release pathways remain available. It becomes more dangerous when the dam is already relying on fewer structures. A weak snow year is manageable when reservoirs are high. It becomes more dangerous when the previous year ended near a critical threshold. Vulnerability is created by combinations. Lake Powell is removing the separation between them. The people living farthest from the dam may never see the white bathtub ring, hear the turbines, or stand beside the exposed boat ramps. Yet the decline can still reach them through a utility bill, an irrigation assessment, a tribal infrastructure budget, a food price, a reduced environmental program, or a hotter home. That is the system hidden behind the water level. The small part capable of fracturing it is not the concrete wall stretching across Glen Canyon. It is the remaining vertical distance between the lake and the openings through which the entire network expects the water to pass. Each foot of that distance has become infrastructure. Each foot is electricity, flexibility, stored time, and another chance to survive the next dry year without forcing one community to protect itself by transferring the loss to another. Lake Powell is often presented as a local water story, a problem belonging to the American Southwest, a reservoir hidden among red sandstone cliffs that matters primarily to the states connected directly to the Colorado River. That interpretation is understandable, but it is no longer sufficient. The reservoir has become something much larger. It is one of the clearest demonstrations of how modern civilization responds when an entire environmental baseline begins to shift. The true story is not simply that one lake is lower than it used to be. The story is that an entire system, built across generations using assumptions that once appeared reliable, is discovering that those assumptions are gradually losing their predictive power. Every major piece of infrastructure begins with a belief about the future. Engineers estimate how much rain will fall, how much snow will accumulate, how often floods will occur, how much electricity people will consume, how quickly cities will grow, and how rivers will behave over many decades. Those assumptions become blueprints. Blueprints become dams, canals, reservoirs, power stations, highways, neighborhoods, irrigation districts, and legal agreements. For much of the 20th century, those assumptions worked well enough because natural variability remained within the range that the system was designed to tolerate. Dry years arrived, but wet years restored storage. Reservoirs dropped, but they recovered. Cities expanded, but the river usually supplied enough water to keep pace. The Colorado River system was designed around this balance. It was never intended to eliminate drought. It was designed to survive drought by storing the surplus from wetter years. That distinction is critical because the strategy succeeds only if wet years continue producing enough surplus to replace what dry years remove. When the surplus itself begins shrinking, the entire operating philosophy changes. Reservoirs no longer function primarily as savings accounts that accumulate abundance. They begin functioning as emergency reserves that are repeatedly drawn down faster than they can be replenished. That transition is exactly what Lake Powell now represents. The reservoir is revealing that resilience depends not only on engineering, but also on the environmental assumptions behind that engineering. A dam can remain structurally sound, while the climate conditions supporting its intended operation gradually change. Concrete does not have to crack for the system to become less resilient. The river simply has to deliver less usable water than expected over enough consecutive years. This idea extends far beyond the Colorado River Basin. Around the world, infrastructure built during the 20th century is increasingly confronting conditions outside the statistical range that shaped its design. Flood control systems are facing rainfall events more intense than historical averages. Coastal defenses are confronting higher sea levels. Electrical grids are adapting to longer heat waves and greater cooling demand. Transportation networks are experiencing repeated damage from extreme temperatures, floods, and wildfires. Agriculture is adjusting to altered growing seasons, changing snowmelt timing, and more frequent water shortages. Lake Powell is therefore not an isolated anomaly. It is part of a much broader pattern in which infrastructure remains physically present, while the environmental rules governing its operation gradually evolve. The reservoir also illustrates another defining characteristic of complex systems. Stress rarely remains where it begins. A weak snow season develops in the Rocky Mountains. Soil moisture declines. Runoff decreases. Reservoir elevation falls. Hydropower production becomes less secure. Electricity prices may increase for some utilities. Agricultural costs rise. Water managers negotiate emergency releases. Legal disputes intensify. Communities revise long-term planning. Financial uncertainty grows. What began as reduced mountain runoff ultimately influences sectors that appear completely unrelated to mountain weather. This is the hallmark of systemic risk. Individual components may continue functioning, but their growing interdependence allows stress to travel farther and faster than most people expect. Another important lesson emerging from Lake Powell concerns the idea of the new baseline. Human beings naturally compare present conditions with personal memory. If a reservoir rises after one wet winter, it appears to be recovering. If it falls again after another dry year, the decline appears temporary. This way of thinking assumes that the historical average remains the destination toward which the system will naturally return. But climate science increasingly suggests that in many regions, the average itself is changing. A new baseline does not mean every year becomes worse than the previous one. It means the entire distribution shifts. Wet years still occur. Dry years still occur. Floods still happen. Snow still falls. But all of those events now unfold within a warmer atmosphere, a thirstier landscape, and a more heavily developed watershed. Imagine climbing a staircase inside a building while the entire building is slowly descending on an elevator. Individual steps still move upward, yet the building as a whole continues moving downward. That is one way to understand the Colorado River today. Strong snow years still lift Lake Powell. Exceptional runoff still provides relief. But if the underlying climate continues increasing evaporative demand while water use remains high, each recovery begins from a lower platform than previous generations expected. This is precisely why a single favorable winter cannot be interpreted as proof that long-term challenges have disappeared. The system may improve while the baseline continues shifting beneath it. Water management across the American West is increasingly adapting to this reality. Cities have invested heavily in conservation, wastewater recycling, leak reduction, efficient landscaping, and improved water planning. Many urban areas now use less water per person than they did decades ago despite significant population growth. These achievements demonstrate that adaptation is possible. They also demonstrate that urban conservation alone cannot solve the basin's imbalance. Municipal use represents only one portion of total Colorado River consumption. Agriculture remains the largest user, supporting food production across vast regions. Changes in agricultural water use involve economic livelihoods, rural communities, national food supplies, and legal water rights that developed over more than a century. Any long-term solution, therefore, requires balancing environmental reality with economic and social realities. That balance is extraordinarily difficult because every proposed adjustment creates winners and losers. Reducing irrigation may preserve reservoir storage but affect farm income and food production. Holding more water upstream may protect hydropower while increasing pressure downstream. Expanding groundwater pumping may provide temporary relief while creating future depletion. Building new infrastructure may improve local resilience while requiring enormous financial investment. There is no single engineering project capable of restoring the 20th century river. Instead, the basin faces a series of continuous decisions about how limited water should be allocated under changing environmental conditions. The Colorado River Compact itself illustrates this challenge. The legal framework dividing the river between the upper basin and lower basin was negotiated using hydrological information that later proved more optimistic than the river's long-term average supply. At the time, the available data appeared reasonable. The negotiators were not acting irrationally. They were working with the scientific understanding of their era. But modern observations and paleoclimate research suggest that the river has often carried less water than early 20th century measurements implied. Combined with population growth and warming temperatures, that historical overestimation means the basin has been attempting to distribute more water on paper than nature consistently provides. Lake Powell sits directly within that tension. Every decline in storage makes the difference between legal expectations and physical reality more visible. The reservoir is no longer simply balancing seasonal runoff. It is balancing decades of accumulated assumptions against contemporary hydrology. Another systemic challenge emerges from the increasing frequency of emergency management. During the 20th century, emergency reservoir operations were expected to remain exceptional. They existed for unusual circumstances rather than ordinary planning. Today, however, emergency measures have become increasingly familiar. Temporary agreements, voluntary conservation programs, interstate negotiations, supplemental releases from upstream reservoirs, drought contingency plans, and revised operating guidelines now occur with much greater regularity. Emergency actions remain effective because they buy time, but they also reveal that the system is using extraordinary tools more often than originally intended. A society can respond successfully to one emergency. It can even respond successfully to several. The concern arises when emergency procedures gradually become the normal method of operation. At that point, resilience begins to erode, because resources reserved for exceptional events are repeatedly consumed by ordinary conditions. This process resembles a family relying on emergency savings every month to pay routine household expenses. The savings account delays financial collapse, but it also shrinks continuously because income no longer matches spending. Eventually, even a modest, unexpected expense becomes difficult to absorb. Lake Powell is approaching that same financial logic in hydrological form. Stored water has become the emergency account supporting annual operations. Each weak runoff year requires another withdrawal. Each successful intervention spends part of the reserve intended for future uncertainty. That is why the coming year carries such significance. The greatest threat is not necessarily that next winter will be dry. Nature has always produced dry winters. The greater threat is that another disappointing runoff season would arrive after much of the available flexibility has already been consumed protecting the present one. This is how systems cross thresholds, not because one event is unprecedented, but because ordinary stress arrives after resilience has already been depleted. The concept applies equally to reservoirs, electrical grids, hospitals, transportation systems, forests, and financial markets. Resilience is not measured by performance during ideal conditions. It is measured by the ability to absorb repeated shocks without losing essential function. Lake Powell suggests that the Colorado River Basin is entering a period where repeated shocks matter more than isolated extremes. A moderately dry year following several difficult years may produce greater consequences than an exceptionally dry year following a decade of healthy storage. Sequence becomes as important as severity. This is another characteristic of the new baseline. The order of events increasingly determines outcomes because safety margins have become thinner. A strong winter followed by another strong winter can restore confidence rapidly. A weak winter, followed by another weak winter, can erase years of careful planning. The basin is becoming more sensitive because its operating buffer has diminished. Yet the story is not one of inevitable collapse. Complex systems also possess remarkable adaptive capacity when societies recognize changing conditions early enough. The Colorado River Basin has already demonstrated significant innovation in conservation, interstate cooperation, scientific forecasting, reservoir modeling, environmental restoration, and public awareness. Satellite observations now monitor snowpack, soil moisture, groundwater, and reservoir levels with extraordinary precision. Climate models continue improving seasonal forecasting. Water recycling technologies expand every year. Agricultural efficiency continues advancing. Urban conservation has repeatedly exceeded expectations. These developments matter because adaptation rarely arrives through one dramatic invention. It arrives through thousands of coordinated improvements that gradually reduce vulnerability. The challenge is that adaptation requires accepting the existence of a new baseline before crisis forces every decision. Waiting for Lake Powell to reach minimum power pool before fundamentally adjusting long-term planning would be similar to waiting until a bridge begins collapsing before scheduling inspections. The warning exists precisely so that action can occur beforehand. That is why Lake Powell deserves attention beyond the American Southwest. It is showing how advanced societies respond when environmental change unfolds gradually rather than catastrophically. The reservoir is not asking whether civilization can survive. It is asking whether civilization can adapt before the remaining margin becomes too small. Every exposed foot of canyon wall represents more than missing water. It represents another reminder that infrastructure built for one version of the world is now learning to operate within another. The question is no longer whether the West can endure a single dry year. It is whether an entire network of water, energy, law, agriculture, ecology, and urban development can successfully redefine normal before the old definition disappears completely. The closer Lake Powell moves toward a critical threshold, the easier it becomes for the story to separate into two extremes. One side treats every decline as proof that the reservoir is about to vanish, the dam is about to fail, and the American West is days away from losing water and electricity. The other side points to every wet winter, every temporary rise in elevation, and every emergency intervention as proof that the danger was exaggerated from the beginning. Neither interpretation matches the evidence. The real situation is more complicated and in many ways more serious, because the strongest warning does not require an apocalyptic claim. Several facts are firmly established. Lake Powell is operating far below full pool. Its elevation has been declining during a year when natural inflow is projected to reach only a fraction of the historical average. Minimum power pool, near 3,490 feet, is a genuine engineering threshold. Below it, Glen Canyon Dam can no longer produce hydropower normally, and its capacity to release water becomes more constrained. These are not speculative claims, and they do not depend on a distant climate model. They are measurements of the reservoir, forecasts based on observed snow and runoff, and physical limits determined by the design of the dam. It is also well established that rising temperature reduces Colorado River flow by increasing evaporation and evapotranspiration, particularly through changes involving snow, soil, and vegetation. Research has estimated that mean discharge declines significantly for each degree of warming, although the exact percentage varies with the method, location, and period being studied. This does not mean temperature controls every fluctuation in the river. It means heat consistently pushes the water balance in one direction. When precipitation is weak, warming deepens the loss. When precipitation is near normal, warming can prevent more of that water from becoming runoff. When precipitation is abundant, warming can reduce the size or duration of the recovery. That relationship is real. Another real connection is the relationship between Lake Powell and Lake Mead. Water held back to protect Powell cannot simultaneously raise Mead. Water released to support Mead reduces Powell's elevation. Additional water moved from upstream reservoirs may protect Glen Canyon temporarily, but it lowers storage elsewhere. The basin is not creating water through operational decisions. It is deciding where a limited amount of water will be stored, when it will be released, and which risk will be carried by which reservoir. This trade-off is the central reason the current situation should be treated as a system problem rather than a single lake emergency. Yet several common claims go beyond what the evidence supports. Lake Powell approaching minimum power pool does not mean the reservoir is approaching complete emptiness. Minimum power pool and dead pool are not the same threshold. At minimum power pool, normal hydropower production is lost, but a substantial volume of water can remain behind the dam. Dead pool occurs lower, when gravity can no longer move water through the dam's available outlets in the ordinary way. Confusing these two elevations creates a false image of the lake, suddenly becoming a dry canyon the moment the turbines stop. The actual danger is not that all water disappears at once. It is that useful functions disappear in stages while water is still visible. It is equally misleading to claim that crossing minimum power pool would automatically cause a widespread blackout. Glen Canyon hydropower is important, especially because it can respond quickly to changing demand. But the Western electrical grid contains many other sources and transmission connections. Utilities could purchase replacement power. Grid operators could compensate. The effect would more likely appear first as higher costs, reduced flexibility, and greater vulnerability during periods of extreme demand. That is serious. But it is different from claiming that millions of homes would immediately go dark. Accuracy matters because exaggeration gives skeptics an easy target. When the most dramatic prediction fails to occur, the underlying risk can be dismissed, even though it remains unresolved. Another unsupported claim is that one dry runoff year can be attributed entirely to human-caused climate change. Weather patterns still matter. Storm tracks, ocean conditions, atmospheric circulation, precipitation timing, and natural variability all influence a particular winter. Climate change does not select every storm or directly dictate the snowpack of one specific season. Its role is to alter the background conditions in which those events occur. A dry year unfolds across a warmer landscape. Soil moisture is often lower. Atmospheric demand is higher. Snow may melt earlier. More water can be lost before reaching the river. Climate change loads the conditions, but it does not eliminate natural variability. The reverse claim is also false. The existence of natural drought does not mean warming is irrelevant. Tree ring records show that the Southwest experienced severe megadroughts long before modern greenhouse gas emissions, but that history does not protect the present system. It proves that the region is naturally capable of long drought. Adding human-caused warming to that natural capacity increases moisture loss and intensifies the consequences. Natural variability and climate change are not competing explanations in which only one can be true. They can operate together, with one producing a dry sequence and the other making that sequence hotter and more damaging. There are also claims that remain genuinely uncertain. No forecast can state with complete confidence the exact elevation Lake Powell will reach on a specific future date. Reservoir projections depend on snowfall, spring temperature, soil moisture, water demand, releases, conservation measures, and operational decisions that may change as conditions evolve. The most probable forecast is not a promise. A wetter than expected season could raise the lake. An even weaker runoff could lower it faster. Major federal intervention could alter the path. Forecasts should therefore be understood as scenarios showing what will happen under particular assumptions, not as prophecies carved into stone. That uncertainty does not make the forecasts useless. It tells managers how wide the range of possible outcomes has become and how much protection is required against the worse ones. It is also too early to know exactly how prolonged operations below minimum power pool would affect every component of Glen Canyon Dam. Engineers understand the major hydraulic limitations, but the precise performance of outlet structures under extended low elevation conditions would depend on flow rates, maintenance, sediment, vibration, water quality, and operational modifications. It would be irresponsible to declare that the dam would fail. It would be equally irresponsible to assume that secondary outlets can replace normal turbine operations indefinitely without cost or complication. The honest position lies between certainty and dismissal. The dam has alternatives, but fewer alternatives mean less resilience. The reservoir contains water, but less usable elevation means fewer functions. Intervention can buy time, but it cannot guarantee that the next winter will restore the water used to create that time. The most credible danger is therefore not a cinematic collapse. It is a progressive narrowing of choices. Hydropower becomes weaker before it disappears. Replacement electricity becomes more expensive before shortages occur. Upstream reservoirs are drawn down before they become emergency stories of their own. Lake Mead receives less protection as Powell is defended. Negotiations become harder as each party realizes that preserving its own security may transfer risk to someone else. Then another dry year arrives, not as an unprecedented event, but as an ordinary event, landing on an extraordinary lack of buffer. That is what the evidence proves. Lake Powell is not guaranteed to cross minimum power pool. It is not guaranteed to remain above it. One wet winter could improve the outlook, and one weak winter could make it much worse. But uncertainty over the exact date does not erase the underlying trajectory. The basin is warmer, runoff efficiency has declined, storage remains depleted, and the system is operating closer to thresholds that once seemed remote. The responsible conclusion is neither that collapse is inevitable, nor that concern is exaggerated. It is that the Colorado River system has entered a condition where normal variability can produce abnormal consequences. The risk is real, not because the worst outcome is certain, but because the margin protecting the system from that outcome has become dangerously thin. The white line surrounding Lake Powell will remain long after the next storm passes. It will remain if the reservoir rises. It will remain if boat ramps reopen, if turbines continue turning, and if a wet winter pushes the immediate danger farther into the future. The cliffs will still record the height of the water, the system once considered normal. That is why the image matters. It is not merely a scar left by drought. It is a boundary between two different versions of the Colorado River, one remembered by the infrastructure and another now arriving beneath it. Lake Powell may recover from this descent. A powerful snow season could send more water through the upper basin, rebuild part of the lost elevation, increase hydraulic pressure at Glen Canyon Dam, and restore some of the operating margin that has disappeared. Emergency conservation could slow the decline. New agreements could distribute shortages more deliberately. Engineers could modify outlet systems. Utilities could replace lost generation. Farms and cities could reduce demand, and the basin could gain more time. None of those outcomes is impossible. The Colorado River system is not helpless, and its future has not been decided by one forecast. But recovery must not be confused with resolution. A rising reservoir would change the immediate numbers without automatically repairing the mechanism that produced them. The landscape would remain warmer. Dry soil would still intercept snowmelt. The atmosphere would still demand more moisture. Legal promises would still exceed the river's reliable supply in many years. Lake Mead would still depend on water passing through Glen Canyon. Upstream reservoirs would still contain only a limited amount of emergency storage. The same network would remain connected to the same shrinking source. A wet year could lift the lake, but only a new balance between supply and demand could protect the system. This is the central message left by the approaching power threshold. Lake Powell does not have to become empty to change the West. It only has to fall low enough that water can no longer perform all the tasks assigned to it. The turbine does not care how large the reservoir appears from an aircraft. It cares about elevation and pressure. The irrigation district does not care that millions of acre-feet remain trapped behind sandstone walls if the cost of moving water becomes unaffordable. The household enduring a heat wave does not experience climate change as a global average. It experiences it through the price of cooling, the reliability of electricity, the availability of water, and the capacity of local institutions to respond. The crisis becomes real at the smallest point where the system can no longer deliver what people assumed would always be available. That point may be a turbine intake. It may be a pumping station, a farm contract, a tribal water project, or a utility budget. Large systems often reveal their weakness through small components. Lake Powell is showing those components one by one. It is also showing that the future will not arrive as a single announcement. There may be no morning when officials declare that the old Colorado River has ended and a new one has begun. The transition will appear through revised forecasts, lower release schedules, emergency meetings, reduced power production, altered planting decisions, and another foot disappearing beneath the white ring. Each change may seem temporary. Together, they form the new baseline. That is why the most important question is not whether Lake Powell crosses minimum power pool next month, next year, or not at all. The more important question is how close a vital system should be allowed to operate to physical failure before society treats the warning as permanent. A civilization built around reservoirs cannot control every winter. It cannot command snow to fall or force runoff through dry soil, but it can decide how much water to promise, how much storage to preserve, how quickly to reduce demand, and whether emergency measures become a bridge toward adaptation or merely a way to delay it. Those choices will determine whether the next dry year becomes another difficult season or the moment when several hidden weaknesses finally connect. Lake Powell will continue to rise and fall. The river will still produce wet years, and relief will still arrive. That possibility is real, and it matters. But the reservoir has already delivered a warning that no future rise can erase. The system was designed to use stored water to survive temporary drought. It is now being asked to use temporary wet years to survive a long-term shift. The direction has reversed. The safety margin has become the resource being consumed. One day, the water may climb high enough to cover part of the white ring again. The turbines may keep turning, and the immediate crisis may disappear from the headlines. But the question exposed on the canyon walls will remain. How long can a system built to store the past continue operating when the river beneath it is becoming something the past never prepared it to hold?